All right, let's begin. It's nice that I don't have to recopy these examples. We'll just get them all done here. Also, I posted the quiz 1, a blank version, and the answers. And in general, what you're going to want to do is every time I do something like that, you do not go directly to the answers. You're going to go to the blank version. You're going to redo your quiz, anything you got wrong, redo it before actually looking at the answers. You definitely want to prioritize what you can do on your own as opposed to read someone else doing. That being said, let's just get these guys out of the way quickly so we can get on with our lives. How do I do that? Yeah?
So it's cinch.
Yep. You need the chain rule there. Just to check if you remember that the derivative of cosh is sinh. How do we do this one? Product rule. Okay, so there's two things multiplying. So we know we need the product rule. We actually wrote that down last time. So you differentiate one thing, you leave the other thing. So the derivative of this is? Leave that alone. Plus, leave that derivative of this. That's cosh. And neither of them take a minus sign. So that was the difference. And can't really do anything else there. See. So just me reminding you of the product rule and all that stuff. How do you do this? Yeah?
U prime over U.
It's u prime over u. So this is our u in this case. And what's u prime?
Secant sinh.
Hyperbolic secant squared over that guy. Can we simplify that? Is that simplifier? Get anything nice out of this?
It turns to secant h over sine or sinh.
Where?
Or
Come again?
secant h of x over sinh of x.
It's not much nicer, is it? You just think that. E. How you differentiate phi to the sinh. Yeah?
It's the derivative of ax. It's the same format, so it's 5 to the power of sinh x times ln 5.
Times the cosh, right? So you need the chain rule. Right, so you apply the chain rule to the a to the u, it's u prime a to the u ln a, where a is a constant greater than 0. Moving over here. We do this one. You use the quotient rule, there's division. It also bring the x upright as x to the minus 1, do the product rule. Almost a matter of preference, but I think the quotient rule tends to work out nice enough. So what do we get? Simplifying right now. F. How do you find the integral of tangent? You don't?
You substitute, right? You substitute?
Substitute what?
Is it the formula? 1 minus tangent squared x equals secant squared x, and then,
Sure, we don't have a tangent squared.
Can't you turn it into sinh over cosh, and then substitute?
It's an identity. This is the definition of tangent is sinh over cosh. Now what?
You can substitute sinh x for u, and then take the derivative of that for cosh x.
No, you
Or
don't
sorry,
have
vice versa.
It's the other way, right? You have 1 over cosh x, so that's not going to do good. So your u will be cosh. Your du is going to be that sinh dx, which is what you have right here. So you end up with 1 over u du, pretty much directly. Integral of that?
ln of absolute value.
Absolute ln of absolute value of u plus c, and then you just replace the u with what it is. So that's ln of absolute value cosh plus c. Technically, you don't need the absolute values here because your cosh is always positive, but it's not wrong to leave them. You could be wrong by forgetting them, so just leave the absolute values in, even though you might not need them. Can you figure out this one? E to the 2x over 1 minus e to the 4x. What was that? Who did that? Yeah?
That u equal to e to the 2x.
Your du would be?
2e to 2x.
So you can say 1/2 du is equal to e to the 2x dx. And so this guy would become what?
Integral of 1 over 1 minus u squared. Halving of 1. du.
What's that?
Inverse hyperbolic
Right,
tangent.
it's literally right there. So that's tangent inverse. That's your integral. We'll actually see another way to integrate 1 over 1 minus x squared, and it's not difficult to prove that the answer that we'll get with the technique I'm going to show you in the future is actually going to be equivalent to this, because you can express sinh and cosh as exponentials, and so their inverses are going to end up having logarithms in it. And the new way I'm going to teach you to do that a couple weeks from now, you'll see that we'll get logarithms in the formula. It's not actually different, it's actually the same thing. Tangent just gets you an answer more efficiently, but it's by no means necessary. So these are the hyperbolic functions that I introduced last time, as well as some calculus rules. It's cool to know them, not terribly essential, but they're nice to know. So, that being said, let's actually begin. So, last class was a warm-up and getting everything, getting some loose ends tied up, getting hyperbolic functions out of the way, but let's actually do what we're here to do in Calculus 2. So, Calc 1, you spent a lot of your time on limits, derivatives, and applications of derivatives, and you do a little bit of integration at the end. You also covered the fundamental theorem of calculus, and now we're going to complete, well, not really, but we're going to complete the foundation of integral theory in terms of how do you actually compute integrals. So, that's probably a nice way to think of part 1. The theme for part 1 is fundamental integration techniques. So, we are going to be focusing on this for the next few weeks, just learning how to integrate more difficult and difficult things, and finding nuances and challenges with integration, which will far exceed the challenges with differentiation. So, picking up where Calc 1 left off, not going over the Calc 1 stuff, so I do expect you to be familiar with basic integration rules as well as integration by substitution. So, now I'm going to present to you the art of integration. So we're going to call it an art because unlike with differentiation, integration has its nuances. There's nothing that's going to... It's very rare that you have like a strategy that covers pretty much every generic example of that thing. So there's some art to it, and we'll talk about how to actually get this done. So if I throw a random integral at you, how do you know what you want to try first or second or third or fourth? So it turns out that you still started the way that Calc 1 started things. So given a random, I was going to say random integral, let's say Calc 2 integral. There's going to be a way you want to approach things. So you have a random integral, the integral of f of x dx. Whenever you see such an integral, your mind should start going through a certain type of thought process. And the first 3 steps of this thought process are always going to be the same thing. Step 1. I'm going to try to apply a basic rule. What are the basic rules? So back in Calc 1, you learned a bunch of derivative rules. You also learned the fact that you can look at every derivative rule as an integration rule in reverse. You learned how to differentiate as well as integrate just basic elementary functions. So I'm talking about the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c if your n is not equal to minus 1. You learned about the integral of 1 over x, which means your n equals minus 1 is equal to ln of absolute value of x plus c. You learned that the integral of your sine of x is minus cosine of x plus c. You learned that the integral of secant squared of x dx is equal to tangent of x plus c. You learned the integral of, it's another nice one, 1 over 1 plus x squared dx is equal to tangent inverse plus c, etc. Right? So you have all these basic rules that tells you how to deal with very specific basic functions. These we will call our basic rules. They just tell us how to integrate very basic things. Okay? So you see a random integral, the very first thing you're going to try to look at is, does the basic rule I have apply to this integral that I'm looking at? Right? Is there some template that I can, it just fits on top of everything exactly, and it's really nice. That's it. Not much more to do there. So it's basically, remember, you also have integration properties. So if you have a sum of 2 of these things, you can apply the rule one at a time. If you have a constant times any of these things, you can apply the constant. So not much to say about the basic rules. Step 2. So if step 1 works out, great, you're fine. Then step 2, what if step 1 doesn't work out? What if this thing doesn't actually look like a basic rule? The next thing you're going to try is to try to simplify it so it looks like a basic rule. Or just simpler in general. You'll tend to want to simplify things either way. But just give you a random example here. Let's say I give you the integral of, like there was one on the quiz which I don't have a blank, but let me just make up another one. Say 4x squared minus 3x plus 1 all over x cubed dx. So you look at that, doesn't look like any basic rule, you know, that's a very weird, well not weird, some random rational function. You don't have a basic rule that looks like that, so what do? Panic. No, you don't panic. All you do, you say, well, it doesn't look like a basic rule that I have. can I simplify it so that it looks like basic rules that I have? So the first thing you're going to do is notice that, well, there's a single term in the denominator. Let me actually divide it into each thing. So you can actually get 4x squared over the x cubed minus the 3x over the x cubed plus the 1 over the x cubed. You probably skip this step in practice, I guess. So this would give you 4 over x. This would give you 3x to the minus 2. This will give you x to the minus 3 dx. And now what you realize is that this now looks like some basic rules that you have. That's the 1 over x guy right there. Of course, you could factor out the 4. These two have the form x to the n. So here this is going to be 4 ln of absolute value of x minus add 1 to the power, divide by the new power. Here, add 1 to the power, divide by the new power. Let's see. And so that would be your answer. So step 1, does a basic rule apply? Like with no work on my part, can I just apply some template? Step 2, that doesn't work. Can I simplify it? Can I do some algebra mumbo jumbo to get to a simpler form? So a lot of times that will work, in the beginning anyway. Now step 3. Try a substitution. That's always step 3. It's always the third thing you think about. Okay. So step 1, does a basic rule apply? No. Okay. Can I simplify it to get a basic rule? No. Okay. Does a substitution work? Right. Always the third question you're going to ask yourself. And of course you know about substitution. Okay? So I'm not going to explain that right now. So you're going to try to find a substitution and you know the nuances of choosing a substitution. 1, you want to choose to substitute an entire expression with a single variable. That will make the entire integrand simpler. A rule in Calc 1 was that you have to be able to find the derivative somewhere else in the function. That's no longer true. We're going to look at situations where you won't have that, but we can integrate with substitution anyway. But ultimately, you want to substitute it for the purpose of transforming what you're looking at to look like one of these basic rules. Except you change the variable in terms of u or t or something else. So that's substitution. Okay. So that's where Calc 1 steps off. Now, after this point, the steps are in no particular order. There is no generic way to look at anything. However, these are always the first 3 things you think of. No matter what level you're at, firstly, you see a random integral. Is it basic? No. Can I simplify it to be basic? No. Can a substitution work? It's always the first 3 questions. After that, it's a toss-up, right? And I'm going to teach you how to actually choose one over the other. So we're going to kind of complete this list where there's approximately a step 4 with certain caveats and certain patterns that you look for. But we're going to complete this list. So I'm going to give you a bunch of other techniques that we can use to populate this kind of approach towards integrals. And I'm going to tell you when you would want to choose a certain thing. Maybe while we're going on, or maybe at the end I'll just wrap up. Okay, after all these techniques, how do you know which one you want to pick? Because that's what's going to be confusing. You have a random integral, you don't know what you want to do. You don't want to go down the wrong path because you can get into a lot of trouble. Now, to that end, finally we can get to talk about something new. But you always want to start at the basics and work your way back up. So the first 3 things that should go through your mind at any point should be these 3 things. Here is one of the other options. So as far as I'm concerned, this is the start of our syllabus. We're going to do section 8.2. It's called integration by parts. So this is a new technique. So we all know what substitution is. It was the reverse of the chain rule. Chain rule is a very useful rule from derivatives. And when you try to do that backwards, integration by substitution is what happens. Now, what we're going to want to do is reverse the product rule. is there a way to do the product rule backwards? Turns out there is. So, I remember what the product rule says. Well, if I have two functions f and g, I want to take their derivative. It's going to be f prime g plus f g prime. Now, here's what I'm going to do. I'm actually going to integrate this equation. I'm going to take the integral with respect to x on both sides. Integral is distributed across some, so I can do that. Now, what you'll have on this side, according to the fundamental theorem of calculus part 1, the derivative and the integral cancel each other out. Right? You're going to get, of course, a plus c, but you know what I mean. There's going to be, imagine there's going to be a plus c on the right side somewhere. But the left side is going to pretty much simplify to f times g. And now what we're going to do is we're going to solve for one of these integrals on the right side. Now, in general, it doesn't really matter which one you pick, but I'm going to pick the one that makes it nicely fit with the traditional formula that's used. So I'm going to solve for this one. Solve for that one. And you would get f times g minus the integral of f prime g dx. Now, we usually don't use f and g to state this rule. So let me do a notation change, but hopefully that's not going to mess anyone up. We're going to set f of x, of course there's an x here that I'm not writing, equals u. I'm going to set the function g of x equals v. This of course means if I differentiate both sides, f prime of x dx is going to be du, right? Because du dx is going to be f prime. I can multiply both sides by dx. We can do that with the Leibniz notation. And our g prime dx is going to be dv. And I'm just going to rewrite that same formula with u's and v's instead of f's and g's. So writing the above, we obtain the integral of f, which is u, g prime dx is dv, is equal to f, which is u times v minus the integral. Our g is v, I'm going to write that first, v du. The integral of u dv is u times v minus the integral of v du. This is our formula. This guy is what's called the integration by parts formula. Now gives us a new way to do an integral. So basically this formula says, to compute this integral, I just have to compute the right side. And of course you're going to notice there's another integral on the right side. The idea is, the integral on the right side hopefully is going to be easier to compute than the integral on the left side, right? And there are going to be rules and strategies that we put in place to kind of ensure that that has the best chance of happening. So, let's actually do an example. Let's say I wanted to integrate x times e to x. That's what we're going to do. So what's the first thing I want to do here?
Pick a U and a V.
Huh?
Pick a U and a V.
No, the first thing you do Is there a basic rule that applies to this integral?
No.
Second thing you do, right? No. Second thing you do,
Can you simplify?
is there a way to simplify this so that basic rule applies?
No.
No. Third thing you do, can a substitution work?
No.
Well, kinda. It's just that the substitution is going to put us in a situation where we actually don't know how to continue. You could actually do a substitution here. You could do something like u equals x, always a bad substitution. I hope I'll never see anyone trying to say u equals x. Like you literally just rewrite everything in terms of u. Technically, you could do u equals e to the x. Your du would be e to the x dx. And you can go in, you can swap everything out. You'll end up with the integral of ln of u involved here. But the thing is, we don't have to integrate ln of u. So for the moment, we shall say substitution won't work. It could, technically. If you know how to integrate the natural log, which, fun fact, to figure out how to integrate the natural log, you use integration by parts. It's kind of a chicken and eggs problem here. So the first three steps can't work, right? But it's always the first thing you think about. Basic rule? No. Can I simplify that? No. Substitution? Gets worse. Okay. Now we're doing something else. Now I realize, okay, I have a product of two functions, and you can kind of think of this like maybe there's an f and a g, okay? Or more specifically, one of these is going to be a u, the other one is going to be a dv. So, now you know I'm going to try integration by parts. What would you choose to be, how are you going to set up this left side on top of this, is that you're going to choose the parts. That's why it's called integration by parts. You're going to choose parts to be u and dv, so that you can set up this left side of the integral to get that to fit on top of this, and then you're going to fill out the right side based on the choices that you've made here. So what do you want to do? Who do you want to choose for u and dv?
U is x.
So in this case, you chose that, okay, that's going to be my u. This whole thing here is going to be the dv. These are the parts, we call them. Right? So that's called integration by parts. You pick parts and you kind of work them into this formula. Now, of course, I need to know what du is going to be, and I need to know what v is going to be, so I'm going to differentiate this. My du is going to be, well, dx. And if I integrate this, my v is going to be e to the x. Of course, ignore the plus c, we'll put it on at the end. And so now what I'm going to do is I'm going to plug these all into the formula. So the integral of x e to the x dx is going to be equal to u times v minus, just by following that formula, the integral of v times du. And it turns out that this integral can be computed by computing that expression. Now, we'll notice that this integral over here is actually pretty easy. In fact, that's a basic rule. That's something you can do without, just by memorizing a formula. Integral of t to the x is c to the x plus c. And that's your answer. And of course, you can check that. You differentiate this part with the product rule. You're going to get x e to the x plus e to the x. Differentiate this, you're going to get another e to the x of e to the x is cancelled. And differentiate a constant, you'll end up with x e to the x as the answer. You differentiate that, you will get that one. So that's actually the integral. Now, here is a word of caution for the uninitiated, which is probably most of you. It matters who. Right? What if we had went the other way? Right? Suppose I had x e to the x dx, and I chose u equals e to the x, and the dv equals the x. What would have happened is you'd have gotten du equals e to the x. Here you'd have gotten v equals x squared over 2. And then what you would have gotten is that this integral would end up being equal to, according to the integration by parts formula, which is over here, u times v minus the integral of v times du. And if you look at this integral over here, that's worse than what we started with. That actually went in the wrong direction, right? And x e to the x, that's got to be easier than x squared e to the x. You just actually made your life harder. So, with that being said, does anyone know how you would choose? Right. So, how do you choose? So if you know you're going to do an integration by parts, you need to know how to choose the parts, so you don't end up going down the wrong road and actually shooting yourself in the foot, right? Now, how you would come up with this is just basic trial and error. You do a bunch of problems and you kind of figure out just how things would tend to work out in your favor most of the time. Luckily for us, people have done this and they came up with a nice mnemonic for actually choosing how to choose, right? So there's a mnemonic here. It's called Liate. Now, there are many versions of this. There's Liate is another one. The T and the E are kind of interchangeable, but in general, this is kind of the order in which you want to choose. Now, let me explain the mnemonic to you. L stands for logs. I stands for inverses, as in inverse trig. Right, so if like a sine inverse or cosine inverse, and L stands for log, like an ln shows up. A stands for algebraic. Right, but that basically means polynomials. But Liate doesn't really roll off the tongue. Right? You want a vowel in there at this point. So when they say algebra or algebraic, technically that's incorrect. Algebraic does not mean polynomial. Algebraic is means a whole other thing, but people just understand it to mean polynomials. T means trig functions, and E means exponential functions. Exponentials. Right, inverted with something. Now, what that means is the guys in the beginning get to be u first. All the way down as you go along gets to be u last. So, by using Liate, you will see that these were indeed the right choices. So, now we don't have many other techniques to compare this to, but again, just to run through this. Boom, this integral shows up on a quiz. You're going to think, does that look like a basic rule? No. Can I simplify it to look like a basic rule? No. Does the substitution work? No. Okay, maybe this is a candidate for integration by parts. And when we have other techniques to contrast that with, I'll tell you why you would choose integration by parts over something else. But now you've settled. I'm going to use integration by parts to attack this. Now what matters is how you choose the parts. You're going to choose based on Liate. What you're going to do is you're going to identify the kinds of functions. This guy here is an A in Liate because it's a polynomial. X is a polynomial. This guy here is an E in Liate. Now, according to Liate, A comes before E, which means the A gets to be the U. This is your U, right? And of course, consequently, the other guy is going to be the dv, right? So that's how you're going to choose. That's going to lead you to saying u equals x and dv equals e to x. Then you go through the whole formula. And when you make the choices based on this, it tends to be the case that the integral on the right side is going to be easier than the integral on the left side. It's not a foolproof method. There are times when integration by parts just won't work. We'll probably do some examples of that later. But when it does work, it's a beautiful thing, and this is how you choose to have the best chance of it actually working. Any questions so far? Yes?
What if when you're integrating, you have something that follows the same letter, the mnemonic, like, I don't know, like, let's say you have like two inverses or like two different logs or something, would you use an
Right, so we're going to do examples like that, actually, and that's where the nuance comes. In fact, the examples I'm thinking of where integration by parts would fail are actually examples like that. If you have two of the same type of function and you choose the parts, no matter how you choose it, you'll kind of go in this loop that never solves anything. It can happen, right? And there are other times where you have two of the same kinds of functions and you can do an integrated by parts and it works out. There's no, like I said, it's not like Calc 1 anymore. There's no hard and fast, oh, this is always going to be fine. Like, no, it might work. It's something to try. And there are times when you have, with enough work, you'll get the intuition of when something might work out versus not. But for now, when I'm teaching you basic integration by parts, it'll tend to be two different types of functions and you choose based on them too. Things will get harder as we move on. Okay, so let's do another example. Integrate that. Okay, so step one, is it a basic rule? No. Can I simplify? No. Substitution work? No. Technically you could do a substitution, but you'll end up with something like, you'll get an e times n, you'll get the ln back because the x is there and the ln is there. So we have no other option at this point but integration by parts, so we know that it's integration by parts. So now that we know that, how do we choose? U equals ln, or dv equals the x squared. Now, that might make some people nervous. Well, dv is the x squared. I'm going to integrate. It's going to become an x cubed. It's going to get harder. Let's just calm down. Let's go with this. Because the ln has a very convenient derivative in this case. What would the derivative here be? 1 over x. And the v here is going to be, yes, it's going to bump up the power, but it's actually going to still work out in our favor. I'm going to do the u times the v, x cubed over 3 of x, minus the integral of the v times the du. And let me write it out. 1 over x times x cubed over 3 dx. So that guy is going to simplify. So the x's are going to cancel. You're going to get the x squared over 3. You can factor out a third. Look at that. That integral looks like a basic rule. So add 1 to the power. You get the cube. Divide by the new power times this 3. You get 1 over 9. Let's see. That's your integral. Questions? Yeah.
Isn't Vx to the third, you put x to the second.
Where?
And the integral says x to the second dx, shouldn't be to the third.
Oh no, remember it's v times du.
Oh,
So
okay.
I took the 1 over x times the x cubed, the x is cancelled. So that's where the x squared comes in.
Thank you.
Yeah. Are we good otherwise? Yeah.
I just have a quick, how many different integration methods are there?
Oh, lots. We're going to cover Integration by parts, we're going to do a bunch of techniques on trig. We're going to do trig sub, we're going to do probably Weierstrass substitution, tabular integration, integration by partial fractions. We're going to cover like 6 or 7. Now, another example. We do that in e to the x times sine of x. So, does it look like a basic rule? No. Did you simplify? No. Substitution? No. Okay, we've gone through that. All right. The only other thing I know is integration by parts, so let's do integration by parts. Okay, so we're going to choose integration by parts. What do we choose here?
Sine 0.
This means your du is going to be cosine. Your v is going to be e to the x. So we're going to get e to the x sine x dx equals 2 u times v minus the integral of v du. Get that.
Keep going.
And we end up with this integral. And then you're going to go through the same thing. Is the basic rule applied? No. Simplify? No. Substitution? No. Integration by parts again. Okay, what are the parts?
Use the cosine.
Equals the cosine. Your du would be minus sine. Your dv would be e to the x. Your v then would be e to the x. And then we're going to have e to the x sine x minus open parentheses. We're going to do integration by parts in here again. U times v. Minus the integral, which now becomes plus the integral, because it's a minus sign here. Minus sign, S-I-G-N.
Yes, sine.
E to the x, sine x.
And you can add it, you can subtract.
And then it up right back where we started.
Or no.
Huh?
Can't you just add it back to the original and then divide it by 2? No. Sorry.
Yeah, you could do that. At this point, you'd stop because clearly you're just going to go into an infinite loop if you continue. So, how do you actually save yourself from this infinite loop? Algebra is basically how you're going to do it. You're going to now look at this like it's an equation. Right? It's like I have A equals B minus C plus A, and I want to solve for A. Right? So I'm just going to add A to both sides. Right? I'm going to, because this is minus A when it distributes, I'm going to add A to both sides. I'm going to get 2A equals B minus C, and then you can solve for A by just saying it's 1/2 of B minus C. And the same way, that's what we're going to do. This is the integral that we care about, which is also that guy. Take him over here, combine terms, you're going to have 2 of them, then I'm going to divide by 2. And so this is going to mean that e to the x sine of x dx is going to be 1/2 e to the x sine of x minus e to the x cosine of x. And of course we know it's an indefinite integral, so there should be a plus c. And that's our answer. So this is another case that you can have with integration by parts. Sometimes it revolves on itself, and you'll start out with something, and you'll end up with the same thing again. And whenever that happens, don't panic. You probably didn't do anything wrong. You can be sure to double check. Once you realize, I definitely did everything right. It doesn't mean something's wrong, just move it to the other side, solve for that algebra. Yeah.
Will that always be the case and it works out like that, that you get the A equals B minus C plus A?
No, like the two previous examples weren't like that.
Like in the case would you have to redo it again?
No.
No.
Because these are nice things. If I had like a e to the 3x sine 2x, then whatever no telling what the constants will end up being. It works out that way because they both have ones in them. It's the first time I'm showing an example like this. I'm not going to make it too complicated. So, yeah, that's how you do this. Yeah.
So if we were to see this problem on an exam or like on the final, the most we would have to do like parts is 2.
No, never said that. It's literally the first time I'm showing you. I'm not going to give you one where you have to do more. Would I? Okay. Now she's giving me ideas. Let's do that one. Doesn't look that scary, does it? We did xe to the x. It's not a big deal. 2 more powers. How much worse could it get? Okay, so basic rule apply? No. Simplify? No. Substitution? No. Okay. Integration by parts, because it's the only other thing here. U and dv. Who's the u?
U is x to the 3rd.
dv equals e to the x dx. du equals 3x squared. v equals e to the x. So, call this I equals u times v minus the integral of v du. And we've got another integral. It's a basic rule apply? No. Simplify? No. Substitution? No. Okay, integration by parts again. Now you're going to choose what are the parts. At this point you're going to come in again. Okay, your u equals the x squared, your dv equals e to the x dx. Your du is going to be 2x dx. Your v is going to be e to the x. So now, I equals x cubed e to the x minus 3, open parentheses, u times v minus the integral of v times du. Now that's a 2x e to the x. There's another integral to do. Okay, let's look at the basic rule. No. Can you simplify it? No. Substitution? No. Integrated by parts again? Can't believe Jhevon gave us 3 integration by parts. Okay, so you're going to go here again. You're going to like, okay, u equals x, dv equals e to the x, du equals dx, v equals e to the x. And at this point, if you're one of those people who always forget your parentheses and stuff, it's starting to get serious at this point. Okay, that's going to be x cubed e to the x minus 3, open brackets, x squared e to the x minus 2, open parentheses. U times v minus the integral of v du. And finally, that's something that we can do easier. That's just going to be e to the x. So at this point, right here, this way, that's just going to be e to the x, we'll see. So at this point, this is going to be x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus, this would be a plus 6 minus 6 e to the x plus c. And that is our integral. 3 integration by parts. Okay. Jhevon would never actually get crazier than that, would he? No way. Quiz would never go further than 3 integration by parts. Then again, it is a night class. I can do whatever I want. I'm the one testing you.
Can you pull down the board so I can see?
Can you just do it twice like the previous one?
Well, yeah, I mean, and we could have done that here, right?
Yeah.
We already computed this. I could have just swapped in my answer at that point. It'd be slightly less annoying. So, all right, let's begin. Nah, no way. Okay. So, integration by parts, very powerful. We did come up with 2 issues so far. One, there's a time when integration by parts can rotate back on itself. In the example I gave you, it took 1 iteration for this to happen, but sometimes it can take multiple. Like you go through this whole list of integration by parts, yet to end up right where you started, kind of demoralizing. And of course, there are times when you just have to take integration by parts over and over and over and just break something down slowly. And there's probably an intuition in here that there's got to be an iterative way to do this, because it does break down somewhat predictably, go from the x cubed to the x squared to the x. Is there a method that kind of could streamline this process for us? And the answer is no. It's just basic no. The answer is yes. We can streamline integration by parts. Enter. Something called tabular integration. Now, while this isn't necessarily a walk in the park, it's definitely going to be better than doing integration by parts over and over and having all these nested parentheses and then having to revolve on itself. And now, after teaching you something like this, I actually won't feel guilty giving you something like that. So, I'm going to explain how it works, then we're going to do some examples. So, tabular integration. So, suppose we have the integral of big f of x times big d of x dx, where I'm going to think of my f as the u and my g as the d. So whatever these functions are, we don't know, but it's just something that I would choose integration by parts to work on. So, I don't know, I guess you can write this down in the margin somewhere. Step 1, you're going to construct a table below it. So, here's how you're going to construct the table. Straight line down here, and you're going to just create a bunch of rows. Now, how many rows? Well, can't tell you in general. It's going to depend. And so you're going to construct a table. Then you're going to repeatedly differentiate and integrate as appropriately. Okay, so the u is the guy that you always differentiate. So I'm going to take f, I'm going to find f prime, then I'm going to find f double prime. Then I'm going to keep going down to f to the nth prime. Right? Now, how many times do I have to take the prime? What is n? I'm going to tell you later, but you're going to keep doing it for a certain predetermined period. I'm going to tell you how to determine it, but this is what the table is going to look like. Then, the dv is the guy you integrate. You're going to repeatedly integrate this. So, I'm I'm going to use subscripts to show integration. So G1, G2, first integral, the second integral, all the way down to the nth integral. Okay? So Gn equals the nth integral of G. 3, multiply along with that. In this fashion, you're going to go from top left to bottom right, top left, bottom right, top left, bottom right, top left, bottom right. Except for the last step, you are going to multiply straight across. Once you get to the last step, you're going to multiply straight across this way. One other thing here, alternating signs. Starting with plus. So you're going to think of this as a positive f times g, then a negative f prime times g2, then a positive this one, then a negative that one, etc. Now when you get to this point in the list, you don't know if it's going to be plus or minus. And consequently, you don't know if this is going to be plus or minus. Just depends on how many rows there are. If it's an even number, it's going to be plus. If it's an odd number, it's going to be negative. Right? And so now, the answer is as shown. Now, once you actually do that, here's how your answer is going to end up looking. This integral is going to be equal to, you're going to be taking all these products with the alternating signs. Now, it's an alternating sign because of these nested parentheses where there's a minus sign always changing the sign of the inside of successive integrals. So, it's going to be positive f times g1. So it's going to be f times the first integral of g minus f prime times the second integral plus f double prime times the third integral, and so on. Minus, plus, dot, dot, dot. Dot, 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 dot. Now, eventually you're going to get to the last part here where you don't know if it's going to be plus or minus. But when you multiply it across that way, you're going to end it with an integral. Right? That's going to be the final integration by parts. So it's going to be the integral of f to the n derivative g to the n dx. And the idea is, if you have the table of the appropriate size, once you get through this process, the integral of the last part is going to be easier than to go the first part. At the very least, it will be an integral where you don't need integration by parts anymore. You might need another thing, you might need substitution, who knows, but you won't need integration by parts anymore. Now let's answer the important question. How big should this table be? Stop when one of three situations are obtained. 1. So one way to know when to stop, if the left column becomes 0. It's one way. So of course, if your f is, say, a polynomial, like an x to the 5th, you keep differentiating x to the 5th, eventually what's going to happen is you're going to get a 0. The moment you get a 0, stop. That's how long the table needs to be. Here's another situation that you would know when to stop the table. If if you get to a row that now it looks just like the original, right? This is going to cover the case when your integration by parts actually revolves on itself. There's going to come a point where you're going to get back the original integral. And so when you read across this row, it's just going to be some constant, perhaps the constant can be 1, times the original integral, right? So it's going to look like the same function all over again. Once a row, so if you don't hit a 0, another possibility is you're going to hit a row that is pretty much a copy of the original row, maybe some constant multiplier in front of it. And when you hit that point, you stop. Now, these two are easy to notice when they're happening. This one does take a little bit of paying attention. If you get to a row that's easy to integrate, and of course, easy can, you know what I mean, right? So eventually, remember how this formula actually ends. It ends with an integral. So if you're doing this, and it's never going to hit 0, and it's never going to repeat to itself, you're just going to keep going until you get to a row where if you read across it, hey, I can integrate that. Hey, I know what to do now. Right? Just have hope. So one day, you're going to get to a row that's going to be, yeah, you're a kind of row. Yeah.
I have a question.
Yes.
Rule 2 says, stop if you get to a constant times the original integral. If you derive the constant one more time, don't you get 0 and you get both of them?
No, it's a constant, not a constant. A constant times the original integrand, which means whatever that function is, it's not going to be a constant. Right, like an example. This is premature, but whatever. I had e to the 2x cosine 3x. And I can differentiate this here. I would integrate, so it's 1/3 sine 3x. Here I would integrate minus 1/9 cosine 3x. Notice this row here is what? It's now minus 4/9 times the original. Right? So it's not a constant. It's not going to go to. It's never going to go to 0.
I just was very close.
Right. It's a constant times whatever the original integrand was. Right. So we started out with an e to the 2x cosine 3x, and we ended up with a constant times e to the 2x cosine 3x. So when I see that happens in this particular example that I just threw out, stop. And that's it. That covers all the cases you'll need to know. Now, in any situation where integration by parts is going to work out for you, this process is going to work out for you. And to sort of prove it to you, what we're going to do is we're going to redo all the examples I already did with tabular integration to show you that all cases are covered. Then we might tackle the x to the 5th, e to the x, and show you how easy it could be. You can go home and on your own time do it the old way and see how you like it. Then I'll give you a bunch of examples because a big part of this class is just drills, just doing a lot of problems and just kind of eventually drilling it into your head. So I'll give you a bunch of examples to do after that, which that might spill into next class, but by next class we'll also get into another technique. And we'll start the quiz on Monday and today. So, what was the first one we had? X times e to the x. Now, if you have a problem where one integration by parts would work, I would just do the integration by parts. But in theory, if a student wanted to, they could just know tabular integration and forget integration by parts and they'll be fine. Like every situation where integration by parts will work, this method is going to work. So, you line it up, of course, so that your u is on the left side. You're going to draw up your table. Differentiate the x. 1. Differentiate the 1. 0. You see that 0. Stop. Right? Now you're going to just integrate this guy until you get to that row. Then it's this times this plus that times that minus and this times this plus integral, but of course that times that is the integral of 0. So this is going to be x e to the x minus e to the x plus, it's going to be the integral of 0. But usually, of course, you know that's just a constant, right? So most of the time we don't even write that. We would just, like, we wouldn't even write this most of the time. We just go straight into the fact that, oh, this is going to be x e to the x minus e to the x plus. Same answer we got before. What about the x? Is it x squared or x cubed? I don't know. X squared, I think it was. So you do this. Of course, to get this to work, you want to actually line it up the other way. You want to put the u first. So I write this as ln of x times the x squared.
Can't you just flip the diagonals?
What?
Can't you just flip the diagonals? So instead of
You
going-
could flip the diagonal, but that's kind of weird.
Okay.
Yeah. Now, one thing you want to do, especially when studying, is you don't want to study for your high-minded, sophisticated, everything's fine brain. Whenever you're studying, you want to study for your stupid, there's a tiger running after me and I'm freaking out, that brain. Every time you add a little bit of complication, it might not seem like a big deal to you now. Oh, I'll just know to flip the diagonal. See, that little thing is going to get you in trouble. When you're under pressure and you don't know what's going on and I'm like, 5 minutes left, and you start freaking out, once you add an extra step to your brain, oh, I now need to do everything just flipped. You're sitting here calm and it seems like, oh, that's not a bad idea. Trust me, when you're in battle, it's a bad idea. Do not add any layers of complication that is not necessary. You memorize it with the diagonals going this way, always do it with the diagonals going this way, every single time. The moment you say, oh, sometimes I'll switch it, recipe for disaster. And it seems like innocent, but trust me, it's not. Right? So you want to study for your freaking out brain, right? So you're like, oh, I think that'll be fine. Yeah. Whenever you're saying that to yourself, check yourself. Like, no. Like, do it the most simplistic way that maintains, like, the structure of how you learned it in the first basic case, right? You always want to do that. So I always want the diagonals to go this way. I'm not going to mess up rewriting that, but I'll mess up with the diagonals and the sign changes and going the other way. Right? So, yeah, so I'm going to rewrite it like that. Differentiate this one time, I can see that if I integrate that one time, I immediately get a row that's easy to integrate, like a multiply across, this polynomial, right? Now, of course, two things are going to happen. One, I know once I differentiate the ln, I'm never going to get an ln back, right? You keep differentiating an ln, you're just going to keep getting 1 over x, then 1 over x squared, then 1 over x cubed with some constant, right? So I'm never going to be in the case where I'm going to get the original back. I'm also never going to be in the case where eventually one of these guys are going to go to 0. That's never going to happen. So now I know that I'm looking for a row to be easy. So I'm not going to like go down here a few steps and then go down here. I'm going to do 1 and 1. This, then that. Okay, not easy. This, then that. Not easy. This, then that. I'm going to really watch for when that row comes up. And in this situation, it happens after one iteration. But again, I'm going to multiply along the diagonals. This times this, which is a plus minus that times that integral. So this becomes x cubed over 3 ln x minus the integral of this times that. And that's easy to do with. And that's the answer we got last time. So those two were the easy situations. Let's look at the revolving situation. Again, the basic one that we looked at. Integral of e to the x sine x. So again, you go through the 3 steps in your head. Doesn't look like a basic rule, can't simplify. Substitution is not going to work. I'm going to do integration by parts. You can set up the table. Right? Now, you should immediately be aware of a couple things. Neither of these are going to hit 0 when I keep differentiating them, and I don't see them getting any easier. The e to the x is not going to get any simpler for sure, and the sine of x is just going to keep bouncing between sine and cosine. So I kind of have a feeling that it's going to repeat on itself here, and so I'm going to integrate that, differentiate that, integrate this, differentiate that, integrate this. And now you'll notice I have a constant times the original. I have -1 times the original if I multiply across. So at that point, you stop, right? And we're going to do this times this, plus that times that, minus, and then plus the integral of this. So this is going to be equal to plus this times this, which means a minus e to the x cosine x. Minus this times this, well, it's a minus times a minus. That's going to give me a plus e to the x sine x. Plus this integral, the integral of this product, which gives me back a minus e to the x sine x. And at that point, you'll see that that's the original. I got the original row back, I'm going to get the original integral back. And here it's fleshed out, there are no parentheses to have to worry about, everything's kind of laid out without parentheses. So now you see that I can just move this to that side and divide by 2. And of course, that's what we got the first time around. Yeah.
Shouldn't the sign, shouldn't the sign of x be the u? Like, do we need to?
It could. Like I said, the t and the e, you can kind of switch them without much thought. In fact, another mnemonic instead of liate is actually Liate, where logs, inverses, polynomials, exponentials, and trig functions, where they switch the e and the t. It actually doesn't matter that much. But the first part, that's definitely important. The t and the e can be switched. That being said, if you remember Liate, switch it, right? I can think of 2 things because I've been doing this for a really, really long time. You're new to it, always do it Liate. Okay. Now, let's just jump and do the x to the 5th e to the x. Now, hopefully at this point you can appreciate how annoying that would be using a regular integration by parts with the nested parentheses. How annoying is it going to be with tabular integration? It's probably going to be a long table, but other than that, x to the 5th e to the x, to write it a little bit smaller. I'm going to set up the table. Now, you're going to get 5x to the 4th, 20x cubed, 60x squared, 120x, 120, 0, stop. Here, you're going to just integrate this guy, so it's just e to the x being repeated. That one's easy enough. Just keep going until you get to this row. And then you're going to do those diagonals. This time it's the which that last one is just going to give you a plus c. So now you just write them off. X to the 5th e to the x minus 5x to the 4th e to the x plus 20x cubed e to the x minus 60x squared e to the x plus 120x e to the x minus 120 e to the x plus c. That's your answer. Hopefully you can appreciate how annoying that would have been had I not done the table. You'd have like 5 nested parentheses that you'd be combining like terms to get to this point. Yeah, that took us a few seconds. So that'll take you forever if you're not paying attention to join the class later. I'm sorry for the confusion. We're going to join the class on Monday. I'm going to throw this on the quiz and they're going to It's like the whole quiz they're working on that one problem. Yeah. Tabular integration. It always works. You could even learn this in place of integration by parts, and you'll never really suffer for it. In fact, it's exactly integration by parts. It's just a way to streamline it. It's like a pro level. It's like, instead of like adding something on your calculator, just doing the forms in Excel. Yeah, just put on your shades and more. This is like the Excel version of integration by parts. No. We're probably not going to get through them all, so I'm going to list a bunch of examples. We'll do as many as we can. You finish up the rest for Monday, which will also be good practice for the quiz. Integral. Let's learn how to integrate ln. Seems like about time. Damn it. It's about time to learn to integrate ln. Okay. Let's integrate the inverse sine function. How about we integrate e to the square root of x? Which seems like a strange thing to be able to integrate. Remember, we can't integrate e to the x squared. Impossible. We can actually do this, right? It looks scarier, but that's actually doable. This is impossible. I'll probably put that later in the list. Let's do x cubed e to the x squared. Let's do x squared e to the x cubed. Do x cubed sine of x squared. To square root of x, cosine times square root of x. Let's integrate arctangent. Sometimes copy those on and then go into it. And once we complete these examples, we'll move on to the next section. Right? Okay, go. Do you have a suggestion? Yeah? Exactly.
That q equal to ln x and dv equal to 1.
Yeah. It's a very sneaky way to do it, isn't it? Just think of the other function as 1. Some of you are probably like, how's integration by parts going to work? There's no parts. Yeah, there's always another part. There's always like a multiplication by 1 here. So that would you think of as an A, that you think of as an L. Right? So you would choose u equals ln x. And your dv would be equal to 1 dx. Now, once you kind of figured you have to use integration by parts, that's kind of obvious, because you would never choose the dv to be the ln, because you'd have to integrate the ln. And if you could do that, you would just integrate the ln, right? So the ln has to be the part you differentiate, because you don't know how to integrate it. So the du is going to be 1 over x dx, and the v is going to be x. And so this is going to be equal to u times v minus the integral of v du. 1 over x times x dx. So this is the u dv. And these cancel. That's x ln x minus the integral of 1 dx. So that's just x ln x minus x plus c. And thusly, we now have a new inductee. We welcome them into the prestigious company of our basic rules. From now on and forevermore, you know how to integrate ln. I don't expect you to ever have to actually do this in practice. Now on, this is a basic rule that you know. The integral of ln x is x ln x minus x plus c. Putting that in a box because from now on, that's a formula you know. That's how you integrate ln. I expect you to remember that. We're going to derive it once, just to show you where it's coming from. But from now on, that's something you know now. That's the integral of ln x. How would you do that one? Yeah? Yeah, kind of the same thing. You might have, I don't know how to integrate that, and I don't think I can simplify that, or it's not a basic rule, so you probably do integration by parts because it's the only thing we've done, but what are the parts? Again, the other part is 1. So 1 would be A, and this is an I, inverse sine function. So your u is going to be, of course, inverse sine function. Not only because of Liate, but because we don't know how to integrate it. It has to be the part we differentiate. What is the derivative of this guy? And v is going to be equal to x. So this is going to end up being equal to u times v minus the integral of v du and we end up with that. Okay, how do we continue? How do we do that integral?
So can we not do substitution and then solve for u to get the x?
Yeah, substitution. Right. What we're doing is, yes, you can have a problem that you'll have to use multiple techniques. Again, the idea is, every time you see a new integral, you start from scratch. Just because you're in integration by parts mode doesn't mean integration by parts is the only thing you're going to need. A new integral pops up, start over. Can I use a basic rule? Can I simplify it? Can I substitution work? This guy's substitution is going to be what we want to do. So what do we want to substitute?
X squared.
1 minus
No.
x.
What is x?
U equals 1 minus x squared. It's a very calc one way to do it. But we're big kids now. Let's do a u squared substitution. Now, why would I do a u squared substitution? Because I don't want to have to worry about half powers. Right? If I make under here a u squared, then it's going to kill that 1/2 power. Right? Now that idea is something that we're going to build on as time goes on. When you're doing a substitution, you don't always have to substitute a single variable. The point of a substitution is to make everything easier. So you can substitute a u cubed for something, or a u to the 5 or 7 for something. Whatever's going to make the thing look nicer, you can substitute it. So here I'm going to do a u squared substitution. Or maybe I'll do both. Let's do it both ways. Let's do a u substitution. We'll go through it. You'll see how it would look. Then I'm going to do the u squared substitution, and you're going to see how it would look then. Your du here is going to be minus 2x dx. So you're going to have minus 1/2 du is equal to your x dx. So this integral is going to be equal to, so your integral of x over the square root of 1 minus x squared dx is going to be equal to minus 1/2 the integral of 1 over radical u du. How do you integrate that?
Can't you make it u to the negative half power? And just do it.
And that's going to become
1/4 u to the half power.
So you add 1 to the power, which gives you a positive at half, divide by the new power. So you get 2, which is going to cancel this, it's going to become minus that. C. So this actually is going to become just the negative square root of 1 minus x squared. Plus. And you can swap that in. Now, just for comparison, and this isn't even a nice integral to do. You're going to see sometimes it's going to make your life a whole lot easier. We'll definitely do examples a bit later on. Just want to gently introduce you to this new idea for some of you. So compare this to the following. So if I have the integral of x over the radical of 1 minus x squared dx, what I can do is a u squared substitute. Now you just differentiate like normal. Derivative of u squared is 2u. Derivative of this is minus 2x. And so what you end up getting is that minus u du is equal to that x dx. Now if you go in and you start plugging all that in, this x dx is now minus u du over the radical of 1 minus x squared is just going to actually be u. You just have to integrate 1. Right? It's already a lot nicer, as you can see, but it really starts to shine when you have radicals all over the place. Right? Yeah, integral of that is just u. What is u? It's the square root of that guy, minus 1 minus x squared. So ultimately, the integral of sine inverse is x sine inverse of x. Well, that would be plus, because it's minus the minus. The radical of 1 minus x squared. C. And from now on, that's not a basic plus minus. Even I don't remember that off the top of my head. It doesn't show up often enough to remember that. Integral of ln, you should remember that. Integral of sine inverse. Take a couple minutes to do it, it's going to be fine. But that is the integral. But yeah, you can try things like that. We'll see more examples. But like even try to do, say, x over the cube root of 1 minus x squared. And try to do a u cube substitution. See how you like it. interesting. How do you do this? E to the square root of x. Ideas?
Is the little part?
Okay, and what would happen?
So then if the ones apart, then you would set the square root x as the u and then you differentiate that.
Slide nicer? No. That's actually not that bad. You can actually dig yourself out of this hole, but prevention is better than cure, so let's not get into it in the first place. Now, surprisingly, the first step here, if you want something a little bit nicer psychologically, is a substitution. Now, I'm not going to use a u substitute. I'm going to do a different verb, t. Some people getting anxious. Derivative isn't there. We don't have derivative. That's not a thing anymore. Don't worry about it. Right? Sometimes you go with a substitution. Is a substitution going to work? Nah, let's try it. Right? E to the radical x, complicated. E to a single variable, nicer. It's worth a shot. Substitution, the point is make it look nicer. So having a radical in the power is a very weird thing to have. How about we get something that's not a radical in the power? Like a t. What I can do now is, again, can even be a little bit more sophisticated here. Let's square both sides to do a t squared substitution. What's going to happen now is I will get 2t dt is equal to 1 dx. So this is going to become the integral of, well, it's going to be e to the t, because that's now my radical x. What is the dx going to be? Well, 2t dt. In other words, this is 2 times the integral of t dt. And that guy, we know how to deal with that. How do you do that? By parts. That's actually the first example we did. It's equivalent to x e to the x. So that's going to be t e to the t minus e to the t plus c. So that's going to be 2 times radical x e to the radical x minus e to the radical x plus c. So insert. So you start off with a substitution to kind of tame things a little bit, because you have these radicals all over the place, they kind of make things more confusing. So you start off with a substitution, get the radical out of there, and you'll end up in a spot where it looks nicer in some sense, but it requires something a little bit more than a substitution. It requires integration by parts. That's the guy. Okay, what do you want to do here? Ideas?
Substitute x squared.
sub tx squared. So, if you forgot to go through the motions of, is it a basic rule? And you might be tempted to jump directly into integration by parts here. Make this the u and make that the dv. Problem is, what's the integral of e to the x squared? Can't do it, right? So a substitution first is actually the way to go. What would you substitute? Well, this guy is impossible. So maybe getting rid of the square is going to be a good idea. So I'm going to do that. T equals x squared.
Square root of t.
So now, differentiate both sides. This is dt is equal to 2x dx. What you will notice is that my x cubed, well, I can actually write that as an x squared times an x, right? So that part here is my 1/2 dt. That part here is my t. That part here is my t. So it becomes the integral of t e to the t times 1/2 dt. In other words, 1/2 times integral of t e to the t. There's that guy again. At this point, we might have inadvertently memorized this. This is t e to the t minus e to the t equals c. But this time your t is not radical x, like in the last example. Your t is actually x squared. So this is equal 1/2 x squared e to the x squared minus e to the x squared. Let's see. What's that answer? What was that? That was D. And we're out of time. You guys do the rest. I'll see you guys on Monday. So our quiz on Monday is going to cover what I talked about on Monday. So I'll give you a little quiz on what are they called, hyperbolic functions. Although after that I'll probably never quiz you on them again, but I'll quiz you on it next week, as well as integration by parts. Other than that, enjoy your weekend, work hard, and remember, homework is already up for anyone whose first day is here. Follow the instructions on the class website to access it and get started working on it.